Welcome to Dark Cosmos Theory, where we explore the deepest mysteries of space, time, and the fundamental nature of reality itself. Before we dive into today's mind-bending topic, if you're enjoying this journey through the cosmos, please hit that like button and subscribe to the channel. It helps us continue bringing you the most fascinating discoveries and theories from the cutting edge of physics and cosmology. And hey, drop a comment below letting us know where in the world you're watching from. We love hearing from our global community of cosmic explorers. Now let's venture into one of the most unsettling possibilities that modern physics has ever uncovered. Imagine standing on solid ground, feeling secure in the permanence of the Earth beneath your feet. Now imagine discovering that the ground isn't solid at all, that beneath the surface lies an infinite void, and the only thing preventing you from plummeting into oblivion is a temporary illusion of stability that could shatter at any moment. This isn't just a metaphor. According to some interpretations of quantum field theory, this might describe the actual state of our entire universe. Not the ground beneath your feet, but the fabric of space itself, the laws of physics that govern reality, and every particle that exists could all be balanced on a razor's edge, poised in what physicists call a false vacuum, a state that appears permanent but is actually desperately, terrifyingly temporary. This isn't science fiction. This isn't wild speculation from the fringes of physics. This is a legitimate possibility that emerges directly from our best understanding of how the universe works at its most fundamental level. The false vacuum hypothesis suggests that the cosmos as we know it, with all its galaxies, stars, planets, and life, exists in a precarious state that could collapse at any moment. And when I say collapse, I don't mean gradually fade away over billions of years. I mean instantly, completely, and utterly cease to exist, replaced by a new reality where the laws of physics are so different that matter as we understand it simply cannot be. The most chilling part? If this happens, there would be no warning, no sign, no time to prepare or react. You wouldn't see it coming. You wouldn't hear it. You wouldn't feel anything at all. One moment you'd be reading these words, thinking your thoughts, experiencing the rich tapestry of conscious existence. The next moment, nothing. Not darkness, not silence, but a complete and total erasure of everything that makes you and your universe real. And this could happen right now, or never. We simply don't know. To understand how physics arrived at such a disturbing conclusion, we need to journey into the strange world of quantum fields, where empty space is anything but empty, and where the universe might be playing a cosmic game of chance with stakes we can barely comprehend. We need to understand what vacuum really means, why our current state might be false, and what it would mean for reality itself to suddenly shift into something fundamentally different. This is the story of the false vacuum, and why some of the brightest minds in physics lie awake at night contemplating it. The illusion of empty space. When you look at the night sky, you see stars scattered across vast regions of apparent nothingness. Between those pinpoints of light stretches what we casually call empty space, the vacuum of the cosmos. For most of human history, this seemed straightforward. Empty meant empty, nothing there, a void waiting to be filled. But quantum physics shattered this simple picture, revealing that what we call empty space is actually seething with activity, filled with invisible fields that permeate every cubic centimeter of the universe. These quantum fields are not made of matter or energy in the conventional sense. They're more fundamental than that. Think of them as invisible sheets of potential that fill all of space, waiting to manifest as particles when given enough energy. The electromagnetic field, for instance, exists everywhere. When you add energy to this field in just the right way, you create photons, particles of light. But even when no photons are present, the field itself remains, humming with quantum fluctuations, temporary borrowings of energy from the vacuum that appear and disappear too quickly for us to observe directly. Every type of particle has its own field. There's an electron field that fills all of space. When you see an electron, you're actually seeing a localized excitation of this field, like a ripple on the surface of an infinite ocean. There's a quark field, a neutrino field, and fields for every other fundamental particle we've discovered. These fields overlap, interpenetrate, and interact with each other in ways that give rise to all the complexity we see around us. The screen you're reading this on, your own body, the air you breathe, all of it is just patterns of excitation in these underlying quantum fields. But here's where things get interesting. These fields don't just enable the existence of particles, they determine the fundamental properties of reality itself. The masses of particles, the strengths of forces, the ways different particles interact with each other, all of these emerge from the properties of the underlying fields and how they relate to each other. When we say an electron has a certain mass, what we really mean is that the electron field has a particular configuration that manifests as mass when the field is excited. The vacuum, then, is not truly empty. It's the state of these fields when no particles are excited, when no energy has been added to create matter. But the fields themselves are always there, and their configuration in this lowest energy state, what we call the vacuum state, determines the laws of physics that govern our universe. Change the configuration of these fields, and you change reality itself. Different field configurations would mean different particle masses, different force strengths, different physical laws. Chemistry wouldn't work the same way. Atoms might not form at all. The universe could be transformed into something utterly alien. Now, here's the crucial question that keeps physicists up at night. Are these fields currently in their lowest possible energy state? Or might there be a lower state, a different configuration that would be more stable? If you've ever rolled a ball down a hill, you understand the basic principle. The ball naturally seeks the lowest point it can find. That's where it wants to be. That's where it's most stable. But imagine a ball resting in a shallow valley part way down a mountain. From the ball's perspective, it's at the bottom, at a local minimum. It's stable there, at least temporarily. A gentle nudge won't move it. But if something gives it enough energy to roll over the rim of that valley, it will tumble down to an even lower point, the true minimum. The place it really should have been all along. Quantum fields might work the same way. They might currently sit in a local minimum, a false vacuum, rather than the true vacuum that represents the absolute lowest energy state possible. Our universe would be like that ball in the shallow valley. Stable, yes, but only because nothing has yet nudged it over the edge. And unlike a ball on a hill, the quantum vacuum doesn't need an external push. Quantum mechanics allows for something called tunneling, a process where the fields can spontaneously jump from one state to another without needing enough energy to cross the barrier between them. It's like the ball suddenly appearing on the other side of the valley rim without ever rolling over it. Impossible in classical physics, routine in the quantum world. This possibility that our vacuum state might not be the true vacuum, that the fields underpinning reality might suddenly tunnel to a lower energy configuration. This is the essence of the false vacuum hypothesis. And if it's true, the implications are almost too vast to comprehend. But before we explore those implications, we need to understand why physicists take this possibility seriously. What evidence do we have that our vacuum might be false? And what would cause such a catastrophic transition if it were to occur? The Higgs field and the edge of stability. The story of the false vacuum took on new urgency in 2012 when scientists at CERN's Large Hadron Collider confirmed the existence of the Higgs boson. This discovery was celebrated as a triumph of theoretical physics. The Higgs mechanism, proposed decades earlier, explained how particles acquire mass. The Higgs field permeates all of space, and particles gain mass by interacting with this field. Finding the Higgs boson, the particle that represents excitations of this field, confirmed this elegant theory. But the celebration was tinged with concern, because the measured mass of the Higgs boson, approximately 125 billion electron volts, placed our universe in a troubling position. You see, the Higgs field, like all quantum fields, has a potential energy landscape. This landscape describes how the field's energy changes depending on its value. In our current universe, the Higgs field has a particular value throughout space, and this value sits at what appears to be a minimum in the energy landscape, but calculations using the measured Higgs mass suggest that this might not be the absolute minimum. There might be another, much deeper minimum lurking in the mathematics. A true vacuum state where the Higgs field would have a vastly different value. The current state of the Higgs field is often compared to a valley in the mountains. We're sitting at the bottom of this valley, which is why we consider our vacuum stable. But mathematical models suggest there might be a much deeper valley on the other side of a very high mountain range. We're in a local minimum, not the global minimum. The universe is like a hiker who set up camp in a pleasant valley, not realizing that just beyond the peaks lies a massive crater that represents true stability. From where we are, everything seems fine. The ground is level, the camp is secure, but we're not at the lowest possible point. The height of the mountain range between our valley and the true minimum determines how stable our current position is. If the barrier is high enough, we could remain in our false vacuum state for an unimaginably long time, perhaps forever, for all practical purposes. But if the barrier is too low, or if quantum effects allow tunneling through it rather than over it, then our time in this comfortable valley could be surprisingly limited, and once a small region of space tunnels through to the true vacuum, there's no stopping what comes next. The measurements of the Higgs boson mass were troubling because they placed us near the edge of stability. Other measurements, particularly the mass of the top quark, the heaviest of all known fundamental particles, reinforced this concern. The top quark's mass also influences the shape of the Higgs field's potential energy landscape. And its measured value, combined with the Higgs mass, suggests that we might be living right on the boundary between stability and instability. Small uncertainties in these measurements could push us either way. We might be safe, with a vacuum that will endure forever. Or we might be balanced on a knife's edge, in a metastable state that could decay at any moment. Different research groups have performed increasingly sophisticated calculations to determine the Higgs field's stability. These calculations incorporate quantum corrections, effects from other particles, and improvements in our understanding of the standard model of particle physics. The results have been consistently worrying. Most analyses conclude that with the measured values of the Higgs and TOPS, quark masses, our universe is either metastable, meaning it will eventually decay to a lower vacuum state, or it's right at the boundary between stability and metastability. One influential study published in 2013 calculated that if the measurements were exactly correct, and if there are no new physics beyond the standard model, then our current vacuum state has a lifetime. That lifetime is extraordinarily long by human standards, perhaps 10 to the power of 500 years or more. That's a 1 followed by 500 zeros, a number so vast that it makes the current age of the universe, a mere 14 billion years, seem like the blink of an eye. But cosmically speaking, this is not infinity. It's a finite lifespan for reality itself. The calculation depends sensitively on exact measurements of particle masses. A slightly different Higgs mass might render our vacuum completely stable. Alternatively, unknown particles or forces not yet discovered could stabilize the Higgs field, pushing us away from the edge of metastability. This is one reason why particle physicists continue to search for physics beyond the standard model, not just to understand what else might exist, but to determine whether we're truly as precariously positioned as current measurements suggest. But here's what makes the Higgs field situation particularly unnerving. The calculations don't just say we're near the edge of stability, they say we're close enough that small changes could tip us over. And in quantum field theory, small changes can happen spontaneously. Quantum fluctuations, those temporary borrowings of energy from the vacuum that constantly occur throughout space, could potentially create regions where the Higgs field momentarily achieves a higher energy. And if that fluctuation is large enough, it could trigger the transition we're discussing, a bubble of true vacuum forming in a sea of false vacuum. The Higgs field isn't acting alone in this drama. It interacts with other fields in ways that influence its stability. The strong nuclear force, mediated by the gluon field, affects the energy landscape. So do gravitational effects, especially in regions of intense space-time curvature like near black holes or in the early universe moments after the Big Bang. Every field, every force, every interaction plays a role in determining whether we're truly in a stable state or balanced on the precipice. This interconnectedness means that our understanding of vacuum stability is only as good as our understanding of all the fields and their interactions. We know the standard model incredibly well. Its predictions have been confirmed to astonishing precision, but we also know it's incomplete. Dark matter, dark energy, the matter-antimatter asymmetry, and other cosmic mysteries point to physics we haven't yet discovered. These unknown factors could either save us or doom us. They could provide the stabilization that keeps us safely in our current vacuum, or they could be the triggers that push us over the edge. The Higgs field, then, is not just responsible for giving particles mass. It might also be responsible for the ultimate stability or instability of reality itself. The same field that makes atoms possible, that allows chemistry to work, that enables the existence of stars, planets, and life, might also be the field that could suddenly transform everything into an utterly different form of existence. This is not a comfortable thought, but it's one that emerges directly from our best theories and measurements, and it forces us to confront a deeply unsettling question. If our vacuum is false, what would actually happen if it decayed? The bubble of doom. Let's talk about how the end of everything might begin, not with a bang or a whimper, but with something far stranger. A tiny bubble, smaller than an atom, appearing spontaneously in the quantum foam of space-time. This bubble wouldn't be made of matter or energy in any conventional sense. It would be a region of space where the quantum fields have suddenly shifted to their true vacuum state, a microscopic sphere where reality has changed its fundamental nature. And from the moment this bubble forms, the countdown to universal transformation begins. The creation of this bubble would not require any external cause, no explosion, no cataclysmic event, no intervention from beyond. Quantum mechanics allows for spontaneous transitions through a process called quantum tunneling. Imagine the Higgs field as a marble resting in a shallow bowl. Classically, the marble would need enough energy to roll up and over the rim to escape into a deeper bowl beyond, but quantum mechanically, there's always a tiny probability that the marble can simply appear on the other side of the rim without ever having traversed the space in between. It tunnels through the barrier. The same principle applies to quantum fields. Even though there's an energy barrier between our current false vacuum and the true vacuum state, quantum fluctuations can momentarily borrow enough energy to create a small region of true vacuum. This happens entirely at random, governed by the fundamental probabilistic nature of quantum mechanics. There's no way to predict where or when such an event might occur. It could happen in the depths of intergalactic space. It could happen inside a star. It could happen right here, in the space you're occupying right now. The probability is extremely low at any given point in time, but over the vast expanse of the universe and cosmic timescales, even extremely unlikely events become possible. What would this bubble look like? From the outside, initially, nothing. It would be far too small to see, too small even to interact with normal matter in any meaningful way. But it would be growing. And this is where things get truly terrifying. The bubble of true vacuum would expand outward at the speed of light, not approaching the speed of light, not accelerating toward it, moving at exactly the speed of light from the very instant it forms. Why light speed? Because the boundary between the false vacuum and true vacuum represents a change in the fundamental energy state of space itself. This transition releases enormous amounts of energy, and that energy drives the bubble's expansion. The mathematics of quantum field theory shows that such bubbles expand at the maximum possible speed allowed by relativity. They propagate as spheres of altered reality, growing larger with each passing moment, and nothing can stop them or slow them down. The energy driving this expansion comes from the difference between the false vacuum and true vacuum energy states. Remember, the true vacuum is at a lower energy level. When the field transitions from false to true vacuum, the difference in energy has to go somewhere. Some of it goes into the kinetic energy of the bubble wall itself, driving it outward at light speed. Some might be released as radiation or particles. But the crucial point is that this energy was always there, stored in the unstable false vacuum configuration. The bubble's expansion is simply releasing this stored energy, much like a ball rolling downhill releases gravitational potential energy. As the bubble grows, its surface area increases quadratically. A bubble with a radius of 1 meter has far more surface area than one with a radius of 1 centimeter. This means the amount of energy being released grows rapidly as the bubble expands. And this energy, in turn, ensures the expansion continues. The bubble doesn't slow down. It doesn't stop. It just keeps growing, converting more and more of the false vacuum into true vacuum, releasing more energy, maintaining its light speed expansion indefinitely. Now here's the crucial detail that makes this scenario so apocalyptic. Because the bubble expands at the speed of light, and because nothing, not matter, not information, not even cause and effect, can travel faster than light, there is no possible way to detect the bubble before it arrives. Light carries information. If you see a star explode, you're seeing photons that traveled from that star to your eyes, but those photons travel at light speed. A vacuum decay bubble also travels at light speed. The photons can't outrun the bubble to warn you. No signal of any kind can precede it. This means that even if vacuum decay began at the center of our galaxy, 25,000 light-years away, we would have no idea it was coming. No telescope would detect an anomaly. No unusual readings would appear in our instruments. Space would look exactly as it always has, right up until the bubble reaches us. And then, with no warning whatsoever, the bubble wall would pass through our location, and everything would change. The passage of the bubble wall would not be like any experience you've ever had. It would not be like an explosion reaching you, or a shockwave passing by, or heat washing over you. Those are all events that unfold over time, that your brain could process as they happen. The vacuum decay bubble moves at light speed, which means it arrives at you at the same moment that any signal of its arrival could reach you. There is literally no time between becoming aware of it and experiencing it. No time to think. No time to react. No time even for a single nerve impulse to fire in your brain. One moment, you exist in a universe governed by the laws of physics as we understand them. The next moment, those laws no longer apply. And because the fundamental nature of matter itself depends on the quantum fields being in their current state, the transition to true vacuum would not just change the rules, it would change what matter is, what it can do, how it behaves. Atoms as we know them would cease to exist, not because they're destroyed, but because the fields that define what an atom is have changed their configuration. The particles that make up atoms would have different masses, different interaction strengths. They might not be able to bind together at all. Think about what this means on a human level. Your body is made of atoms. Your brain, your thoughts, your very consciousness all depend on incredibly complex chemical and electrical processes that require atoms to behave in very specific ways. The vacuum state of quantum fields is what makes those processes possible. Change the vacuum state, and none of that works anymore. There would be no neurons firing, no blood flowing, no heart beating. Not because you'd been killed by some external force, but because the fundamental building blocks of your existence would no longer be arranged in a way that permits life or even complex chemistry. This is not death in any conventional sense. Death implies a transition from living to not living, a process that takes time. What we're describing is more like reality shifting to a state where the concept of life simply doesn't apply, where the very substrate that makes life possible has transformed into something else. It's not that you would die in the bubble of true vacuum, it's that you, as a configuration of matter that can think and feel and be, would simply not be possible there. And yet, from your perspective, from the inside, there would be nothing. The bubble arrives at light speed. Your brain processes information using chemical and electrical signals that travel far slower than light. By the time any part of your nervous system could begin to register that something was happening, the fundamental physics that enables nervous systems to function would already have changed. You wouldn't experience the transition. You wouldn't see it coming. You wouldn't feel pain or fear or anything at all. One moment you'd be conscious, the next moment the universe would no longer support consciousness as we understand it. The transition would be so abrupt, so complete, that it doesn't even make sense to talk about experiencing it. This is perhaps the most merciful aspect of this apocalypse scenario, if one can call it that. There would be no suffering, no lingering doom, no time to contemplate what's about to happen. Just an instant transition from existence to something else, something that doesn't include you or anything like you. The bubble of true vacuum would be a sphere of transformed reality, expanding forever at the speed of light, converting the false vacuum universe we know into something fundamentally alien. And we, all of humanity, all of Earth's biosphere, all the stars and planets and galaxies in the region touched by the bubble, would be gone. Not scattered or destroyed, but transformed into forms of matter that our current physics cannot even properly describe. This scenario raises a profound question. If the bubble expands forever at light speed, and if space itself is potentially infinite, what happens to the rest of the universe? Well, the bubble would just keep growing, carving out an ever larger sphere of true vacuum in the sea of false vacuum. But space is big. Really, really big. Even moving at light speed, the bubble would take millions of years to cross a single galaxy, billions of years to cross the space between galaxies. The universe we can observe, our cosmic horizon, extends roughly 46 billion light-years in all directions. A bubble would take 46 billion years just to fill that space. And remember, the universe is still expanding. In fact, it's accelerating in its expansion, driven by dark energy. Depending on where the bubble formed and how the mathematics of expansion versus light speed propagation work out, it's possible that the bubble might never even reach distant parts of the universe. Regions far enough away might be receding from the bubble's origin point faster than the bubble can expand toward them. In that case, some portions of the universe might remain in the false vacuum state indefinitely, never touched by the decay event. This leads to a bizarre picture. Multiple bubble universes, each a region where the fields have transitioned to the true vacuum state, expanding through the larger false vacuum cosmos. Each bubble would have its own physics, determined by the final configuration of the fields in the true vacuum. And these bubbles could never communicate with each other or with the false vacuum regions between them, because signals can't cross the bubble walls. Each would be an isolated pocket universe, forever separated from the rest of existence. But for anyone inside a bubble when it passed through their region, none of this cosmic geography would matter. The expansion rate of the surrounding universe, the existence of other bubbles, the vast reaches of space beyond, all irrelevant. Because by the time the bubble reached you, you'd already be gone, transformed into whatever strange matter can exist in the true vacuum state. The universe you knew would have ended for you, completely and permanently, even if other parts of the cosmos continued on in their false vacuum bliss, unaware of the bubble expanding through their neighborhood of space. This is the bubble of doom, a sphere of transformed reality, impossible to detect, impossible to stop, expanding at the speed of light. It's the ultimate cosmic catastrophe, not because it destroys everything, but because it changes everything so fundamentally that destruction isn't even the right word. It's a transformation of the substrate of reality itself. And according to quantum field theory, it's not just science fiction. It's a real possibility, allowed by the laws of physics as we understand them. The only questions are how likely it is, and whether our universe has already dodged this bullet for billions of years, or whether our time is about to run out. When physics breaks down, let's explore what would actually exist inside the bubble of true vacuum. What would reality look like in a universe governed by different physical laws? This is where our ability to make predictions starts to break down, because the new laws would depend on the exact configuration of fields in the true vacuum state. But we can make some general observations that paint a picture of a cosmos utterly unlike our own, a place where the familiar rules of matter, energy, and interaction have been replaced by something alien and inhospitable to everything we know. First, consider the particles that make up our world. The electron, for instance, has a mass of about 0.51 on 1 million electron volts. This mass comes from the electron field's interaction with the Higgs field in its current state. Change the Higgs field's value and the electron's mass changes too. In the true vacuum, the electron might be much heavier, much lighter, or might not exist as a stable particle at all. The same goes for quarks, the building blocks of protons and neutrons. Their masses would shift dramatically. This has immediate and catastrophic consequences for atoms. The structure of an atom depends critically on the mass ratio between electrons and protons. In our universe, a proton is about 1,236 times heavier than an electron. This ratio determines the size of atoms, the spacing of energy levels, the strength of chemical bonds. Change the masses and atoms as we know them become impossible. If electrons became too heavy, they'd orbit too close to the nucleus, changing the entire nature of atomic structure. If they became too light, atoms would be enormous and unstable, unable to form the tight bonds needed for chemistry. But it gets worse. The forces that hold atoms together would also change. The electromagnetic force, responsible for attracting electrons to the nucleus and repelling electrons from each other, depends on a fundamental constant called the fine structure constant. This constant emerges from the properties of the electromagnetic field in its vacuum state. Change that state, and the strength of electromagnetism changes. The force might become weaker, in which case electrons wouldn't be bound to nuclei at all. Or it might become stronger, crushing electrons into the nucleus in a catastrophic collapse. The strong nuclear force, which holds quarks together inside protons and neutrons, would also be different. In our universe, this force has a very particular strength that allows atomic nuclei to exist. Make it too weak, and nuclei fall apart. Make it too strong, and protons and neutrons fuse together into exotic particles we can't even imagine. The delicate balance that permits hydrogen to exist, that allows helium to be stable, that creates the periodic table of elements we know, all of that depends on the strong force having exactly the right strength. Change it, and the concept of chemical elements might cease to have meaning. Even more fundamental would be changes to the mass of quarks themselves. Quarks come in 6 flavors, but the most important for ordinary matter are up quarks and down quarks, which combine to form protons and neutrons. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. The masses of these quarks, which come from their interaction with the Higgs field, determine the mass difference between protons and neutrons, and that mass difference is crucial for the stability of matter. In our universe, a neutron is very slightly heavier than a proton. This mass difference is small, just about 1.3 million electron volts, but it has profound implications. It means that isolated neutrons are unstable and decay into protons, but inside atomic nuclei, neutrons can be stable because they're bound by the strong force. This balance allows complex nuclei to exist. Change the quark masses and you change the proton-neutron mass difference. Make neutrons much lighter than protons, and you'd have a universe where protons decay into neutrons. Make the difference too large and no stable nuclei could exist at all. The implications extend beyond atoms to the particles of the Standard Model. Neutrinos, the ghostly particles that barely interact with anything, would have different masses. Photons, the particles of light, might not exist as we know them. The W and Z bosons, which mediate the weak nuclear force, would have different masses, changing how radioactive decay works. Even space-time itself could behave differently because the vacuum energy, the inherent energy density of space, would be different in the true vacuum state. This change in vacuum energy might be the most profound effect of all. In our current universe, the vacuum energy is very close to zero, or possibly very slightly positive, which is why we observe the accelerated expansion driven by dark energy. But in the true vacuum, the energy density could be vastly different. It might be hugely negative, which would cause space to contract catastrophically, pulling everything together in a cosmic implosion. Or it might be hugely positive, causing space to expand so rapidly that no structures could ever form. Or it might be some intermediate value, but one that makes the formation of galaxies, stars, and planets impossible through some other mechanism. Let's think about what this means for the universe's large-scale structure. In our cosmos, matter clumps together under gravity to form galaxies, stars, and planets. This process depends on many finely tuned factors. Gravity needs to be strong enough to pull matter together, but not so strong that everything collapses immediately. Electromagnetic forces need to allow gas clouds to cool and condense. Nuclear forces need to enable fusion in stellar cores. Remove any of these pieces and the cosmic architecture falls apart. In a true vacuum universe with different physical constants, none of this might work. Gravity could be unchanged, since it's a property of space-time geometry rather than a quantum field. But without stable atoms, there would be no gas clouds to collapse into stars. Without nuclear fusion, even if stars somehow formed, they couldn't shine. Without chemistry, planets would be amorphous blobs, if they existed at all. The universe would be a dark, structureless void, filled with whatever exotic particles the true vacuum physics allows, but devoid of anything we would recognize as complex structure. And then there's the question of life. Life as we know it depends on chemistry, specifically on the ability of atoms to form complex molecules. Carbon, with its 4 valence electrons, can bond in countless ways, creating the intricate compounds that make up living cells. Water, with its unique properties, serves as the solvent for biochemical reactions. DNA stores genetic information through precise arrangements of molecular bonds. All of this requires atoms to behave in very specific ways, which they do because of the current vacuum state of quantum fields. Change that vacuum state and organic chemistry becomes impossible. Proteins can't fold, DNA can't replicate, cell membranes can't form. Life in any form even remotely similar to what we know simply cannot exist. Now, you might wonder whether some radically different form of life could exist in the true vacuum universe. Perhaps one based on exotic particles or energy configurations we can't even imagine. It's an intriguing thought, but the problem is that life, in the most general sense, requires complexity. It requires structures that can store information, process it, and reproduce. And complexity requires stable systems with many possible states. Everything we know about physics suggests that the configurations of fields that produce such complexity are extremely rare and special. Our universe's laws seem fine-tuned to allow complexity. Change them at random, and you almost certainly get something much simpler and less interesting. This is the deep horror of vacuum decay. It's not just that life would be destroyed, it's that the universe would transform into a place where life is fundamentally impossible, where complexity of any kind might be forbidden by the new physical laws, where the cosmos would be reduced to its barest, simplest state, a featureless expanse governed by rules that permit nothing interesting to happen. The atoms that make up your body, the neurons firing in your brain, the chemical reactions that sustain your existence, all of it depends on the vacuum state being exactly as it is. Change that state and you don't just die. You become impossible as a concept. From a certain perspective, this is more final than any other end we can imagine. If the sun exploded, life on Earth would end, but life could exist elsewhere. If our galaxy collided with Andromeda, the solar system might be disrupted, but the laws of physics would still allow for life somewhere in the cosmos. Even in the heat death scenario, where the universe grows cold and dark, matter still exists. Atoms still form. The rules are still there, even if nothing interesting is happening anymore. But in vacuum decay, the rules themselves change. The foundation of reality shifts to something that prohibits everything we are and everything we could ever be. This is why vacuum decay is considered more than just a cosmic disaster. It's an ontological catastrophe, a change not just in what exists, but in what can exist. The bubble of true vacuum wouldn't destroy the universe. It would transform it into a different universe, one where the very concept of atoms, chemistry, stars, planets, and life has no meaning. Where the fundamental building blocks of reality are arranged in ways that make complexity impossible. Inside that bubble, the cosmos would continue to exist, of course. Space and time would still be there. Particles of some kind would still move and interact. But it would be a universe so different, so alien, so utterly inhospitable to anything resembling what we know, that it might as well be nothing at all from our perspective. And this transformation would happen instantly, completely, with no possibility of reversal. Once the bubble passes through a region of space, that region is changed forever. There's no going back to the false vacuum, no way to restore the old laws of physics. The true vacuum is more stable, lower in energy, is the state the fields wanted to be in all along. Our false vacuum was the temporary aberration, the unstable configuration that couldn't last. And once it's gone forever, replaced by a reality that has no place for us in it. Unresolved, the quantum mathematics of doom. Let's delve into the mathematical and theoretical framework that makes false vacuum decay not just a wild speculation, but a legitimate prediction of quantum field theory. This is where we move from conceptual understanding to the actual physics that keeps cosmologists awake at night. Because vacuum decay isn't something that was invented to scare people. It emerges naturally from the equations that describe how quantum fields behave. And those equations have been tested and confirmed countless times in particle accelerators and astronomical observations. We know they're correct, at least within the domains we've explored. The question is whether they predict our doom. The foundation is quantum field theory, the mathematical language that describes how fields pervade space and how they interact with each other. In this framework, every point in space has a value for each field. For the Higgs field, for instance, there's a number at every location telling you what the field's value is there. In most of space, this value is the same everywhere, about 246 billion electron volts. This uniform value is what we call the vacuum expectation value of the Higgs field. It's the field's resting state, the configuration it settles into when no particles or energy are disturbing it. But why does the Higgs field have this particular value? Why not 0 or 1,000,000 times larger or something else? The answer comes from the potential energy function, a mathematical relationship that tells you how much energy is stored in the field for any given value. Think of it like a landscape of hills and valleys. The field value is like a position on this landscape, and the height represents energy. The field naturally wants to roll downhill to the lowest point, minimizing its energy. Where it settles at the bottom of the valley determines the vacuum expectation value. In our current understanding, the Higgs field sits at the bottom of a valley in this potential energy landscape. It's at a local minimum, meaning the ground is level there and the field is stable. Small perturbations won't move it. But here's the problem. The shape of this potential energy landscape depends on quantum corrections, contributions from other fields and particles that modify the basic picture. And when you calculate these quantum corrections using the measured masses of the Higgs boson and other particles, you find something disturbing. The calculations suggest that the valley we're in, while stable, might not be the deepest valley in the landscape. Far out at much higher field values, the potential energy might drop again, creating another valley that's even deeper than ours. Between our valley and that distant one lies a mountain range, a barrier of higher energy that the field would need to overcome to reach the true minimum. We're stuck in a local minimum, not the global minimum. The field is in a false vacuum state. When there's a lower energy true vacuum state it could transition to. The height of the barrier between these two valleys determines how stable our vacuum is. If the barrier is very high, the probability of tunneling through it is incredibly small. The universe could exist in the false vacuum for timescales longer than we can meaningfully calculate. But if the barrier is low, or if the true vacuum valley is much deeper than ours, the tunneling probability increases. And this is where the measured values of the Higgs and top quark masses become crucial. The top quark mass affects the shape of the Higgs potential through quantum corrections. Heavy top quarks make the potential more likely to develop a second, deeper minimum at large field values. The precise measured value, about 173 billion electron volts, combined with the Higgs mass of 125 billion electron volts, puts us right on the edge. Different theoretical analyses give slightly different answers, but most suggest we're either in a metastable vacuum that will eventually decay, or we're right at the critical boundary between stability and metastability. The tunneling process itself is described by instanton solutions to the field equations. An instanton is a mathematical object that represents a quantum transition from one state to another. For vacuum decay, the instanton describes a bubble of true vacuum spontaneously appearing in the false vacuum. The probability of this happening is proportional to the exponential of the instanton's action, a quantity that measures how much the configuration deviates from the classical behavior. Calculating this action requires solving complex field equations that include quantum effects and the geometry of space-time. The result is typically expressed as a decay rate per unit volume and time. This tells you how likely it is for a vacuum decay bubble to form in a given cubic meter of space during a given second. The numbers that come out of these calculations are extraordinarily small. In simplified models, the decay rate might be something like 10 to the power of minus 500 per cubic meter per second. That's a 1 divided by 10 to the 500, an unimaginably tiny probability. Over the entire observable universe, roughly 10 to the 80 cubic meters, and over the universe's current age of about 10 to the 17 seconds, the probability that vacuum decay has occurred anywhere we can observe is still negligible. But here's where the numbers get tricky. These calculations depend on assumptions about the shape of the potential, the absence of new physics, and the history of the universe. If the potential is slightly different from what we calculate, the decay rate could be much higher. If there are high-energy events that can trigger vacuum decay, like collisions of ultra-energetic particles or the intense fields near black holes, the probability increases. And most importantly, these probabilities are not zero. Over long enough timescales, even incredibly unlikely events become probable. Consider that the universe might exist for trillions upon trillions of years into the future, far longer than it has already existed. Over such timescales, a decay rate of 10 to the minus 500 per cubic meter per second adds up. The cumulative probability approaches 1. Eventually, somewhere in the universe, a bubble will form, and once it does, it spreads at light speed, gradually converting the false vacuum cosmos into true vacuum territory. The universe's age of 13.8 billion years is nothing on these timescales. We're in the early days, the brief period where vacuum decay hasn't happened yet. This leads to another fascinating consideration. If the universe is much larger than our observable patch, perhaps infinite, then vacuum decay might already be happening in distant regions. Bubbles might be forming beyond our cosmic horizon, spreading outward, approaching us at light speed. We wouldn't know. We couldn't know. The bubble wall is the signal. There's nothing that can arrive before it. In an infinite universe with metastable vacuum, vacuum decay isn't a question of if, but when and where. And given infinite space, it's happening now, somewhere, possibly in countless locations. The theory also allows for eternal inflation, a scenario where the false vacuum is constantly spawning new bubble universes through quantum fluctuations. Each bubble expands into its own pocket universe, and these pockets fill the inflating false vacuum background. In this picture, our entire observable universe might be just one such bubble, born from a false vacuum transition in a larger multiverse structure. And that means our universe could itself undergo vacuum decay, creating a bubble within a bubble, nested realities where each level has its own physics. What makes all of this particularly unsettling from a theoretical standpoint is that we cannot definitively rule it out with current observations. We can measure the Higgs mass. We can calculate the top quark mass. We can compute the potential and estimate the stability. But there are always uncertainties, both in the measurements and in the calculations. New physics beyond the standard model could change everything. Supersymmetry, extra dimensions, new heavy particles we haven't detected yet, any of these could stabilize the vacuum or make it more unstable. Some theories suggest that quantum gravitational effects, which occur at the Planck scale, about 10 to the minus 35 meters, might alter the vacuum dynamics in ways we don't currently understand. General relativity and quantum mechanics haven't been successfully unified into a theory of quantum gravity. When we try to calculate vacuum decay rates at the highest energies, where gravity becomes important, our equations break down. We simply don't know what happens. It's possible that quantum gravity stabilizes the vacuum. It's also possible that it makes decay more likely. We're working in a regime where our theories are incomplete. This is the maddening aspect of the false vacuum problem. It's not that we're completely ignorant. We have a framework, quantum field theory, that makes predictions. We have measurements of particle masses that constrain the potential. We can calculate decay rates, at least approximately, but the uncertainties are large enough that we can't say for sure whether our vacuum is stable, metastable with an extremely long lifetime, or metastable with a troublingly short lifetime. The math gives us possibilities, probabilities, scenarios. It doesn't give us certainty. And yet, despite these uncertainties, the core prediction remains. Quantum field theory allows for false vacua. It allows for tunneling between vacuum states. It predicts that such transitions would propagate at light speed as expanding bubbles of transformed reality. These are not speculations. They're consequences of well-established physics. The only question is whether our universe happens to be in a false vacuum, and if so, how long we have before the inevitable transition occurs. The probability paradox. We need to grapple with one of the most perplexing aspects of the false vacuum scenario. The probability is non-zero but unknown. What does that mean, practically speaking? How should we think about a risk that could occur at any moment but might never occur? This is the probability paradox of vacuum decay, and it highlights the strange intersection between quantum mechanics, cosmology, and our human desire for concrete predictions. Let's start with what we know. The decay rate calculations, as mentioned, typically yield absurdly small probabilities per unit volume per unit time. Something like 10 to the minus 500 per cubic meter per second in simplified models. To put that in perspective, you could watch a single cubic meter of space for the entire current age of the universe, and the probability of vacuum decay starting there would still be essentially zero. Even watching all the cubic meters in the observable universe for billions of years yields a vanishingly small probability of decay. But here's where it gets interesting. These numbers are based on our current understanding and measurements, which have uncertainties. The Higgs mass is known to within about 0.1%. The top quark mass has similar precision. But when you propagate these uncertainties through the complex calculations of the Higgs potential, the resulting uncertainty in the decay rate is enormous. A tiny change in input parameters can change the decay rate by factors of 10 to the 100 or more. This means the true decay rate could be much smaller than we calculate, or much larger. Now you might think that averaging over uncertainties would give us a reasonable estimate. But the problem is that the decay rate is exponentially sensitive to the parameters. Small differences in the potential shape don't lead to small differences in the decay rate. They lead to huge differences, many orders of magnitude. This makes it very difficult to pin down the actual risk. We can say that if our measurements and calculations are exactly right, the risk is negligible over observable timescales. But we can't be certain our measurements and calculations are exactly right. There's also the question of rare, high-energy events that might trigger vacuum decay more efficiently than random quantum fluctuations. Imagine a collision between two particles at energies far higher than anything we can produce in particle accelerators. If such a collision created a temporary region where the Higgs field was disturbed to very high values, it might jumpstart the tunneling process. Ultra-high energy cosmic rays, collisions near black holes, or conditions in the very early universe could all potentially serve as triggers. Some physicists have worried about whether particle accelerators, like the Large Hadron Collider, could trigger vacuum decay. The energies involved in LHC collisions are high by human standards, about 13 trillion electron volts. But these are minuscule compared to the Planck energy, about 10 to the 19 billion electron volts, where quantum gravitational effects become important. And they're far below the energies of the most powerful cosmic rays, which can exceed 100 million trillion electron volts. If such cosmic rays haven't triggered vacuum decay, over billions of years, it's unlikely a collider would. But here's the thing, unlikely is not the same as impossible. And when we're talking about an event that would end everything, even astronomically small probabilities take on significance. Consider a thought experiment. Suppose I told you there was a 1 in 10 to the 100 chance that pressing a button would destroy the universe. Would you press the button? Most people would say no. The potential downside is infinite, so even an infinitesimal probability of catastrophe isn't worth it. Yet we live in a universe where vacuum decay has some non-zero probability, and we continue existing, conducting experiments, doing things that involve high-energy physics. Are we pressing the button? The counter-argument is that if vacuum decay were likely to be triggered by anything we can do or observe, it would already have happened. The universe has been around for 13.8 billion years. During that time, countless high-energy events have occurred naturally. Supernovas, gamma-ray bursts, neutron star collisions, particle collisions in the early universe when temperatures were far higher than anything we can create now. If any of these events could trigger vacuum decay, the fact that we're still here suggests they can't. Our continued existence is evidence that the vacuum is stable against anything nature throws at it, at least on these timescales. This is sometimes called the anthropic argument for vacuum stability. If the vacuum were unstable enough to have decayed already, we wouldn't be here to worry about it. The fact that we exist means either the vacuum is stable, or we're very early in the universe's history and have gotten lucky so far, or we're in a region of space that hasn't been reached by a decay bubble yet. It's a curious form of reasoning. Our own existence constrains the probability of past vacuum decay to be zero, at least in our observable region. But it tells us nothing about the future probability. This brings us to a deeper puzzle. If the vacuum is metastable and will eventually decay, why hasn't it happened yet? The universe has existed for a finite time, yes, but it's also unimaginably vast. If you assume the universe is much larger than our observable patch, perhaps infinite, then even tiny probabilities become certainties given enough space. Somewhere, at some time, a bubble should have formed, and once it formed, it should be spreading at light speed. If the universe is billions of years old and many billions of light years across, why don't we see evidence of vacuum decay bubbles? One possibility is that we're simply in a lucky region. The universe is so large that even though vacuum decay might be happening elsewhere, it hasn't reached us yet. The bubbles are out there, beyond our cosmic horizon, spreading toward us but not yet arrived. This is unsettling but not impossible. It means our time might be limited not to the timescale of spontaneous vacuum decay, but to the time it takes for an existing bubble to expand from wherever it formed to our location. Another possibility is that the vacuum is more stable than our calculations suggest. Perhaps there's new physics we don't know about that stabilizes the Higgs field. Supersymmetry, for instance, predicts partner particles for every known particle, and these partners could alter the vacuum potential in ways that make our state absolutely stable rather than metastable. We haven't found these supersymmetric particles yet, but they might exist at energy scales just beyond what we can currently probe. Their existence would solve the vacuum stability problem, along with several other issues in particle physics. Or perhaps the vacuum is metastable, but the decay rate is so much lower than we calculate that it won't happen for timescales far exceeding the universe's current age. If the true decay rate is 10 to the power of 1,000 or more per cubic meter per second, rather than 10 to the 500, then the universe could exist for googles of years, 10 to the 100 years, without vacuum decay occurring. At that point, whether the vacuum is technically stable or metastable becomes almost philosophical. If it won't decay for longer than the universe will remain interesting anyway, does it matter? But the most troubling possibility is that the vacuum is metastable, the decay rate is not absurdly tiny, and we're simply living in the window of time before it happens. This would mean vacuum decay is part of the universe's future, an inevitable end that we can't predict or prevent. And given that the transition would be instantaneous from our perspective, there would be no way to know until it happened. We could be living in the last stable moments of reality as we know it. This uncertainty is maddening. We want to know whether the risk is real or negligible. But quantum mechanics doesn't give us certainties, it gives us probabilities. And when those probabilities involve timescales and spatial scales far beyond human experience, our intuitions fail us. Is a 10 to the minus 500 probability per cubic meter per second negligible? Over human lifetimes, absolutely. Over the entire future history of an infinite universe, absolutely not. The same number can be both infinitesimally small and an absolute certainty depending on your perspective. This is the probability paradox. The false vacuum might decay tomorrow. It might never decay if the calculations are wrong or there's stabilizing physics we don't know about. Or it might decay so far in the future that it's irrelevant to any conceivable concern. We can't tell the difference between these scenarios with current knowledge. And that leaves us in a state of profound uncertainty about the ultimate fate of the cosmos and our place within it. We exist in a universe that might be temporary, poised on the edge of a transition that could render everything we know impossible, and there's no way to know for sure until it either happens or doesn't. The metastability mystery. There's a puzzle that troubles cosmologists when they contemplate the false vacuum scenario. If our universe is metastable, if the vacuum will eventually decay, why hasn't it decayed already? This question becomes more pressing when you consider the universe's history. The cosmos has existed for 13.8 billion years. During that time, it's gone through several distinct epochs, each with different conditions. The earliest moments involved temperatures and energies far higher than anything that exists today. These extreme conditions might have been conducive to triggering vacuum decay, yet here we are, still in the false vacuum. Why? In the first fraction of a second after the Big Bang, the universe was unimaginably hot and dense. Temperatures exceeded 1 trillion degrees. Particles collided with energies billions of times higher than what the Large Hadron Collider can achieve. The Higgs field itself might have been in a very different state, with its value fluctuating wildly across space before settling into the vacuum expectation value we observe today. If vacuum decay were likely to be triggered by high-energy events, this chaotic primordial soup seems like the perfect environment for it. Yet the decay didn't happen. The universe cooled, expanded, and settled into the stable-seeming state we observe. This survival is sometimes called the metastability crisis. If conditions in the early universe were so extreme, why didn't they destabilize the vacuum? Several solutions have been proposed. One is that the universe isn't actually metastable at all. Perhaps our calculations are wrong, or there's new physics that stabilizes the vacuum. This would be the simplest resolution, but it requires us to find errors in our current theoretical framework or discover new particles and forces that change the vacuum dynamics. Another possibility is that the early universe was indeed dangerous, but we got lucky. The probability of vacuum decay might have been higher back then, but still not certain. We're survivors of a cosmic lottery, a universe that made it through the dangerous early period without triggering the catastrophic transition. In an inflationary multiverse scenario, where countless bubble universes are constantly being created, most of them might indeed suffer vacuum decay in their early moments. We just happen to exist in one of the rare bubbles that survived. There's also a fascinating proposal related to inflation itself. Cosmic inflation is a period of exponentially rapid expansion that occurred in the first tiny fraction of a second after the Big Bang. During inflation, space expanded faster than light, smoothing out the universe and setting the initial conditions for structure formation. Some models suggest that inflation might actually protect the vacuum from decay. The rapid expansion during inflation would dilute any small bubbles of true vacuum that formed, preventing them from growing and taking over. Once inflation ended and the universe transitioned to a slower expansion, conditions changed in ways that made vacuum decay less likely. The Higgs field's behavior during inflation is also relevant. During the inflationary epoch, the inflaton field, whatever field drove inflation, was in a high-energy state. This might have influenced the Higgs field's potential, temporarily stabilizing the false vacuum. Once inflation ended and the inflaton field decayed into ordinary matter and radiation, the Higgs potential might have changed again, but by then the universe had cooled enough that vacuum decay became extremely unlikely. In this view, inflation acts as a protective mechanism, shepherding the universe through its dangerous infancy. But there's a flip side to this argument. Some calculations suggest that quantum fluctuations during inflation might have driven the Higgs field to dangerous values in certain regions. Inflation amplifies quantum fluctuations, turning microscopic variations into cosmic-scale structures. If these fluctuations push the Higgs field up the potential hill toward the barrier separating false and true vacuum, they might have increased the risk of decay rather than decreasing it. This remains an active area of research, with different models giving different predictions. Then there's the question of cosmic rays. Since the universe's early days, high-energy particles have been zipping through space, occasionally colliding with tremendous force. The most energetic cosmic rays detected have energies around 10 to the 20 electron volts. That's 100 million times the energy of proton collisions at the LHC. If vacuum decay could be triggered by high-energy events, cosmic rays seem like prime candidates. Yet over billions of years, with countless cosmic ray collisions occurring throughout the observable universe, vacuum decay hasn't happened. This suggests that if our vacuum is metastable, it's stable enough that even extreme cosmic ray energies can't trigger the transition. The anthropic principle offers another perspective. In a multiverse where different regions or different bubble universes have different vacuum states, only those with stable or long-lived metastable vacua can support observers. We find ourselves in a long-lived vacuum not because it's common, but because it's a prerequisite for our existence. Universes with unstable vacua that decayed quickly simply don't have anyone around to ask why. This doesn't explain the underlying physics, but it shifts the question from why hasn't decay happened to we could only ask this question in a universe where decay hasn't happened. There's also a timing argument related to the universe's future. If the vacuum will eventually decay, when might that happen? The current age of the universe, 13.8 billion years, is tiny compared to the timescales involved in vacuum decay. If the decay rate is 10 to the minus 500 per cubic meter per second, then the expected time until decay, averaged over the entire observable universe, might be 10 to the hundreds of years or more. On that timescale, the universe is in its extreme infancy. We're like observers at the beginning of a day, wondering why night hasn't fallen yet. It hasn't fallen because there's vastly more time ahead than behind. This ties into a puzzle about the cosmological constant, the energy density of empty space that drives the universe's accelerated expansion. Measurements show that the cosmological constant is very small but positive. If the vacuum decays to a lower energy state, the cosmological constant would change, becoming negative or just differently positive. The fact that we observe a particular value right now might mean we're in a temporary era where the false vacuum's energy density manifests as the cosmological constant we measure. In the true vacuum, things would be different, but we're not in the true vacuum, at least not yet. The metastability mystery also connects to the hierarchy problem in particle physics. The Higgs field's vacuum expectation value, 246 billion electron volts, is vastly smaller than the Planck energy, about 10 to the 19 billion electron volts. Why is there such a huge difference? Quantum corrections to the Higgs mass should naively push it up toward the Planck scale. That they don't is puzzling and hints at some deeper principle or hidden symmetry that keeps the Higgs light. This same issue relates to vacuum stability. If we understood why the Higgs mass is what it is, we might also understand whether the vacuum is truly stable or merely metastable. Ultimately, the metastability mystery highlights our incomplete understanding of the universe's fundamental structure. We have pieces of the puzzle. We can measure particle masses, calculate potentials, estimate decay rates. But we don't have the full picture. We don't know if there's new physics beyond the standard model that changes everything. We don't know what happened in the universe's earliest moments or how those conditions affected the vacuum state. We don't know whether we're living in a typical universe or a cosmically rare one. And until we fill in these gaps, the question of why the vacuum hasn't decayed yet remains open. A reminder of how much we still have to learn about the cosmos and our place within it. Jushardkri's finality beyond comprehension. Let's compare vacuum decay to other cosmic endings to truly grasp its uniqueness. Throughout the history of cosmology, scientists have proposed various scenarios for how the universe might end. Each is bleak in its own way, but none quite matches the absoluteness of false vacuum decay. Understanding these comparisons helps us appreciate why vacuum decay occupies a special place in our catalogue of cosmic catastrophes. It's not just another way for things to go wrong, it's a category of wrongness all its own. The most widely accepted fate for our universe is called the heat death, or the Big Freeze. This scenario emerges from the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases over time. As the universe expands and stars burn out, energy becomes more evenly distributed. Eventually, after an unimaginably long time, perhaps 10 to the 100 years, the universe reaches a state of maximum entropy. All the stars have died, black holes have evaporated through Hawking radiation. What remains is a cold, dark expanse where temperatures hover just above absolute zero and nothing interesting happens anymore. But here's the key difference between heat death and vacuum decay. In the heat death scenario, the laws of physics remain unchanged. Atoms still exist. The fundamental forces still work the same way. It's just that there's no energy left to drive complex processes. If you could somehow inject energy into this dead universe, you could restart things. Stars could form again. Life could potentially re-emerge. The universe is dead in the sense that it's energetically exhausted, not in the sense that it's incapable of supporting structure. The rules are still there. The game has just run out of moves. Vacuum decay is different. It doesn't run out of energy. It changes the rules. After vacuum decay sweeps through a region, that region can't support complex structures even if you add energy. The fundamental laws that make atoms possible have shifted to different values. You can't restart chemistry. You can't bring stars back. The universe isn't dead in the sense of being depleted. It's dead in the sense of being fundamentally incompatible with the existence of anything complex. The game hasn't run out of moves. The board itself has transformed into something that can't support the game. Another proposed end scenario is the Big Rip. This happens if dark energy, the mysterious force driving the universe's accelerated expansion, becomes stronger over time. In standard cosmology, dark energy has constant density, but if it's instead a dynamic field that increases in strength, the expansion rate of space could grow without bound. Eventually, space would expand so rapidly that it would tear apart galaxies, then solar systems, then planets, then molecules, and finally atoms themselves. Even the fabric of space-time might be ripped apart, leading to a cosmic catastrophe. The Big Rip shares some features with vacuum decay. Both happen suddenly, both are irreversible, and both involve the breakdown of matter. But there's a crucial difference in mechanism and outcome. The Big Rip is a failure of binding. Space expands so fast that forces can't hold things together. But the laws of physics, the values of constants, the nature of particles, all of these remain the same right up until the end. An atom being torn apart by the Big Rip is still an atom experiencing forces as described by quantum mechanics. The rules don't change. They're just overwhelmed by the expansion. If you could somehow stop the expansion, matter would reassemble. With vacuum decay, stopping the expansion wouldn't help. The matter itself has transformed into something else. Then there's the Big Crunch, a scenario where the universe's expansion eventually reverses, causing everything to collapse back together. This would happen if the universe contained enough matter for gravity to overcome the expansion. As space contracts, galaxies collide, stars merge, and eventually all matter is compressed into a singular point of infinite density, perhaps similar to the conditions at the Big Bang. Some models suggest this could lead to a big bounce, where the universe re-expands in a new cycle. The Big Crunch is gradual compared to vacuum decay. You'd see it coming. Galaxies would start moving toward each other rather than away. The cosmic microwave background would shift from red to blue as it's compressed. Temperatures would rise as matter is squeezed together. There would be time, perhaps billions of years, to observe and measure the collapse. And even as things got extreme, the laws of physics would still hold. Matter would behave according to the same rules, just under increasingly intense conditions. The end would be violent but comprehensible. Vacuum decay offers none of these comforts. No gradual build-up, no observable precursor events, no time to prepare or adapt, just an instant transition from one set of physical laws to another. And because it propagates at light speed, entire regions of the universe are transformed in the blink of an eye, cosmically speaking. A bubble expanding for 1 billion years would have a radius of 1 billion light-years, encompassing millions of galaxies, all transformed instantly from the perspective of each location as the bubble wall passes through. There are also more exotic proposed endings, like the possibility of a collision with another universe in the multiverse. In eternal, inflation models, our universe is one bubble among many in a vast inflating space-time. If another bubble collided with ours, the effects could be catastrophic. The collision might compress space, alter field values, or inject enormous amounts of energy. But even this scenario is arguably less absolute than vacuum decay. A bubble collision is an external event, something happening to the universe from outside. Vacuum decay is internal, a transformation arising from the universe's own structure. And collision effects might be localized, affecting only the region where the bubbles meet. Vacuum decay spreads everywhere within the bubble once it starts. Perhaps the closest analog to vacuum decay in terms of finality is a quantum fluctuation that spontaneously destroys all matter. Quantum mechanics, in principle, allows for incredibly unlikely events. All the atoms in your body could quantum tunnel to the other side of the room simultaneously. The probability is absurdly low, but it's not zero. Similarly, the entire universe could quantum tunnel into a state of pure radiation, or something even more exotic. But these scenarios are generally considered so unlikely that they're not worth taking seriously. The probability is exponentially suppressed by the number of particles involved. Vacuum decay is different because it involves a field transition, not a particle-by-particle tunneling event. The mechanism is much more plausible. What makes vacuum decay uniquely terrifying among these scenarios is the combination of three factors. First, it's based on solid physics. It's not a wild speculation. It emerges from quantum field theory, a framework we've tested extensively. Second, it's instantaneous from our perspective. We don't get to watch it unfold or adapt to it. We don't even get to know it's happening. Third, it's absolute. There's no recovering from it, no way to preserve anything through the transition, no refuge elsewhere in the universe. Every other cosmic ending scenario has at least one of these elements missing. Heat death is gradual. The Big Rip might not be based on realistic physics. A big crunch could potentially bounce into a new universe. Vacuum decay has all three, making it the ultimate end of the world scenario. And yet there's a strange kind of peace in its totality. With other cosmic disasters, there's room for despair. You can contemplate the slow fade into darkness of the heat death or the violence of the Big Rip and feel sorrow for what will be lost. But vacuum decay is so complete, so instantaneous that there's no room for suffering. One moment we're here, the next we're not. Not even not in the sense of being dead, but not in the sense of never having been compatible with existence in the first place. It's an ending so thorough that it erases not just the future, but the very possibility of there having been a future. And that perhaps is the most profound difference of all. The deeper implications. We need to step back from the mechanics and mathematics of vacuum decay and confront what it means for our understanding of reality itself. This isn't just a story about a possible future catastrophe. It's a revelation about the nature of existence, the fragility of what we call fundamental, and the possibility that permanence is an illusion we've been fortunate enough not to have shattered yet. Let's explore the philosophical and existential implications of living in a universe where the laws of physics might be temporary. For all of human history, we've operated under certain assumptions about reality. The ground is solid, the sky is above, water flows downhill, fire burns. These regularities led us to conceive of laws, fundamental principles that govern how things behave. As science progressed, we refined these laws, discovering deeper and more universal principles. Newton's laws of motion, Maxwell's equations of electromagnetism, Einstein's general relativity, quantum mechanics. We built a picture of a cosmos that operates according to rules. Rules we can discover and understand through observation and mathematics. But implicit in this entire enterprise was the assumption that these laws are permanent. They might be unchanging through time and space. An electron behaves the same way today as it did 1 billion years ago. The speed of light is the same in every galaxy. The universe might be vast and ancient and filled with mysteries, but at its core, it plays by consistent rules. And this consistency is what makes science possible. We can perform experiments today and trust that the results apply to phenomena tomorrow and in distant reaches of the cosmos. False vacuum theory undermines this assumption. It suggests that the laws of physics are not fundamental features of reality, but rather emergent properties of the particular configuration of quantum fields that happens to exist right now. Change that configuration, and the laws change too. The masses of particles, the strengths of forces, the structure of space-time itself, all of it depends on the vacuum state. And that vacuum state might be temporary, a metastable equilibrium that could collapse at any moment into something completely different. This is deeply unsettling because it means the foundation of reality is not bedrock, but quicksand. We thought we were building our understanding on solid ground, on laws etched into the fabric of existence. But we might actually be standing on a temporary plateau, a configuration that looks permanent on human timescales, but is actually poised to transform. The universe's reliability, its adherence to consistent laws, might be a cosmic fluke, a fortuitous accident of our particular vacuum state, rather than a fundamental property of existence itself. Consider what this means for the concept of natural law. In philosophy and physics, we often speak of laws of nature as if they're inviolable principles that reality must obey. But if the vacuum can decay, then these laws are more like local regulations, rules that apply in our region of field configuration space, but not necessarily everywhere or every when. The true fundamental entity isn't the laws themselves, but the quantum fields that underlie them. The laws are just descriptions of how those fields behave in their current state. Change the state, and you get different laws, equally valid in their domain, but potentially incompatible with everything we know. This challenges our intuitions about what's fundamental. We tend to think that if we dig deep enough, we'll find the ultimate building blocks of reality, the irreducible components from which everything else is constructed. And in a sense, we have found them: quantum fields. But those fields don't have fixed properties. Their characteristics depend on their vacuum state. So the question becomes, what determines the vacuum state? Is there a deeper principle that selects which vacuum configuration is realized? Or is it arbitrary, determined by chance or by initial conditions set at the Big Bang? If it's arbitrary, then the laws we observe are contingent, not necessary. Reality could have been otherwise, and might yet become otherwise. The false vacuum also raises questions about cosmic fine-tuning. The universe we observe seems remarkably hospitable to complex structures. The masses of particles, the strengths of forces, and the properties of space all lie within narrow ranges that allow for atoms, chemistry, stars, planets, and life. Change any of these parameters by even small amounts, and the universe becomes barren. Some see this fine-tuning as evidence of design, or as a consequence of living in one favorable universe among many in a multiverse. But false vacuum theory adds another layer. If our vacuum state is metastable, balanced between stability and decay, then not only do the current values of physical constants need to be fine-tuned for life, but the vacuum itself must be fine-tuned to be long-lived. We need both a universe with the right laws and a vacuum state that doesn't decay before life can emerge. This is double fine-tuning, two layers of improbability stacked on top of each other. Some find this doubling of coincidences more troubling, suggesting we're missing something fundamental about why the universe is the way it is. Others see it as further evidence for a multiverse, where countless vacuum states and field configurations are realized, and we necessarily find ourselves in one that's both life-friendly and long-lasting. The concept of vacuum decay also has implications for how we think about knowledge and prediction. Science is built on the assumption that the future will resemble the past, that the patterns we observe today will hold tomorrow. This assumption, called inductive reasoning, is fundamental to how we learn about the world. But if the vacuum can decay, changing the laws of physics, then induction breaks down. The universe might behave one way today and completely differently tomorrow. Our knowledge becomes radically uncertain, not because we lack information, but because the very structure of reality is contingent and temporary. Now, it's important to note that even if vacuum decay is possible, it doesn't undermine science in practice. The probability of decay at any given moment is extraordinarily small. For all practical purposes, we can treat the laws of physics as constant. We can perform experiments, make predictions, and build technologies with confidence. But on a deeper philosophical level, there's a humility that comes from recognizing that our understanding is built on foundations that might shift. We're not decoding eternal truths. We're mapping out the behavior of a temporary state. This doesn't make our knowledge less valuable, but it does make it more provisional, more tied to the specific conditions of our era and location in the cosmos. The possibility of vacuum decay also touches on themes of meaning and purpose. If the universe can suddenly transform in a way that erases all complexity, all structure, all potential for meaning, then what does that say about our endeavors? Is there futility in building, creating, understanding, loving, if it could all be rendered impossible in an instant? This is not a new question. Humans have always grappled with mortality and impermanence. We know we'll die. We know civilizations fall. We even know, in the heat-death scenario, that the universe will eventually run down. But those endings are at least comprehensible within our framework. They're failures of persistence, not failures of possibility. Vacuum decay is different because it threatens not just existence, but the very framework that makes existence meaningful. It's not that we'll die. It's that the concept of being alive will cease to have meaning in the transformed universe. Our actions, our thoughts, our creations, they matter because they're embedded in a structure of physical law that allows for patterns, for information, for complexity. Remove that structure, and it's not clear what it would even mean for anything to matter. This can feel nihilistic, but it can also be strangely liberating. If meaning isn't guaranteed by the universe, then we're free to create it ourselves, to decide what matters without relying on cosmic validation. There's also a curious parallel between vacuum decay and certain religious or philosophical concepts of apocalypse. Many traditions speak of an end of days, a moment when the current world order is swept away and replaced by something fundamentally new. The Book of Revelation describes a new heaven and new earth. Hindu cosmology includes cycles of creation and destruction. Buddhist teachings speak of impermanence as a core feature of existence. Vacuum decay, in a sense, provides a scientific analogue to these ideas. Not a judgment or a planned transformation, but a purely physical possibility that the world as we know it could end and be replaced by something utterly alien. Physics and metaphysics converge on the recognition that permanence is not guaranteed. But perhaps the most profound implication of false vacuum theory is what it suggests about the nature of stability itself. We think of stable things as enduring, permanent, unchanging. A mountain is stable. The solar system is stable. The laws of physics are stable. But vacuum decay reminds us that stability can be an illusion, a local condition that appears permanent only because we haven't observed it long enough or tested it hard enough. True stability, absolute permanence, might be rarer than we think. Most configurations, most states, might be metastable at best, balanced temporarily, but ultimately doomed to transition. This applies not just to the universe, but to everything within it. Societies seem stable until they collapse. Ecosystems seem balanced until they shift to new states. Even our own bodies are far from equilibrium, constantly using, energy to maintain structure against the tide of entropy. In a sense, we're all living in local false vacua, temporarily stable configurations that will eventually transition to something else. The cosmic false vacuum is just the ultimate expression of this principle, the recognition that even reality itself might be contingent and temporary. So what do we do with this knowledge? How do we live in a universe where the foundations might shift at any moment? Perhaps the same way we've always lived with uncertainty. By valuing the present, by creating meaning where we find it, by loving and building and exploring, even knowing that nothing lasts forever. The false vacuum doesn't change what we should do. It just reminds us, in the starkest possible terms, that existence is a gift, not a guarantee. And that makes every moment we have, every thought we think, every connection we make, all the more precious precisely because it's happening in a temporary bubble of stability, in a cosmos that owes us nothing. Living on the edge. Let's bring this back to Earth, to the practical and emotional reality of knowing about false vacuum decay. How does this knowledge shape how we see ourselves and our place in the cosmos? And what does it mean that we're living in an era where such possibilities are not just science fiction, but legitimate consequences of our best physical theories? These questions don't have easy answers, but they're worth contemplating as we reach the conclusion of our journey into this unsettling corner of cosmology. The first thing to recognize is that false vacuum decay joins a growing list of cosmic threats that we've become aware of as our understanding of the universe has deepened. We've learned about asteroid impacts, gamma-ray bursts, rogue black holes, the eventual death of our sun, and the long-term fate of the universe itself. Each discovery has slightly altered our cosmic perspective, reminding us of our vulnerability and the transient nature of our existence. But false vacuum decay is unique in its combination of absoluteness and unpredictability. It's the ultimate black swan event, something we can't see coming and can't survive. Does this mean we should worry about it? Should vacuum decay keep us up at night? The rational answer is no. The probability of vacuum decay occurring in our lifetimes, or even in the lifetime of human civilization, or even in the lifetime of the sun, is so vanishingly small that it's not worth losing sleep over. There are countless more immediate risks that deserve our attention: climate change, nuclear weapons, pandemics, asteroids. These are tangible near-term threats that we can potentially address. Vacuum decay, by contrast, is beyond our control. If it happens, it happens. There's nothing we can do about it. But emotionally, psychologically, the knowledge of false vacuum decay can still affect us. It's a reminder of cosmic insignificance in the most visceral way. We're not just small compared to the universe. We're contingent. The entire framework that makes our existence possible could collapse at any moment. This can feel disempowering, even depressing. If reality itself is unstable, what does that say about our dreams, our plans, our hopes for the future? Why build or create or care if it could all be erased in an instant? Yet there's another way to frame this. The very fact that we exist, that we can think about such questions, is extraordinary. Against all odds, against the vast improbability of life emerging in a universe that seems largely hostile to it, here we are. Conscious beings capable of understanding, at least in part, the laws that govern reality. We're living in a temporary pocket of stability, yes, but that pocket has persisted long enough for stars to form, for planets to coalesce, for life to evolve, for intelligence to emerge and create art and science and civilization. That's not nothing. That's a cosmic miracle, however temporary it might be. The false vacuum doesn't diminish the value of what we do and create. If anything, it enhances it. Knowing that our time might be limited, that the conditions allowing for complexity and meaning might not last forever, gives urgency and poignancy to our endeavors. We're not building for eternity. We're building for now, for this moment, for this brief window when the universe is configured in a way that makes meaning possible. And that's enough. It has to be enough because it's all we have. This perspective applies not just to humanity, but to all of consciousness in the universe, wherever it might exist. If there are other civilizations out there, they're in the same boat, living in the same metastable vacuum, subject to the same quantum uncertainties, facing the same ultimate unknowns about the nature and duration of reality. We're all temporary guests in a cosmos that doesn't guarantee tomorrow. This shared condition, this cosmic vulnerability, might be one of the most universal features of intelligence in the universe. Everyone who thinks about their place in the cosmos eventually confronts the reality that their existence is not guaranteed by the structure of reality itself. There's also a humbling aspect to this. Modern humans sometimes fall into the trap of thinking we're at the center of things, that the universe exists for us, or that we're the culmination of cosmic evolution. False vacuum theory punctures that illusion. We're passengers in a universe that could change the rules at any moment. Our sophisticated understanding of physics doesn't protect us. Our technology can't save us. We're as subject to the whims of quantum fluctuations as any other arrangement of matter and energy. This humility can be healthy. It reminds us that we're part of nature, not apart from it, and that our fate is tied to cosmic processes vastly larger and more powerful than ourselves. At the same time, there's something empowering about understanding these possibilities. We've come so far in our knowledge that we can contemplate the ultimate fate of the universe itself. We've unraveled the quantum nature of reality, discovered the fields that underlie all matter, and calculated the probabilities of cosmic catastrophes. That's an achievement. Even if we're temporary, even if we're vulnerable, we've managed to understand, at least partially, the rules of the game. And that understanding is itself a form of triumph. We're the universe thinking about itself, contemplating its own nature and potential end. That's profound, regardless of how long it lasts. The false vacuum also invites us to think about legacy in different terms. Usually we think of legacy as what we leave behind for future generations. Our children, our works, our contributions to knowledge and culture. But if the vacuum can decay, then there's no guarantee that any of this will persist. Does that make legacy meaningless? Not necessarily. Perhaps legacy is better, understood as the ripples we create in our own time, the differences we make to the lives we touch, the experiences we have and share. If the present is all we can truly count on, then making the present meaningful becomes the highest form of legacy. This doesn't mean we shouldn't plan for the future or care about what happens after we're gone. Of course we should. The probability of vacuum decay in any human-relevant time frame is effectively zero. We should build as if the future will come, because it almost certainly will. But in the back of our minds, there can be an awareness that nothing is guaranteed, that the foundations are not as solid as they seem, and that this makes every moment precious. Live for the future, but don't take it for granted. Plan as if you have forever, but cherish each day as if it might be the last time the universe is configured to allow days at all. There's also a collective dimension to this. Humanity as a whole faces the false vacuum question. Should it change how we approach our civilization? Should we prioritize immediate concerns over long-term ones, knowing that the very long term might not arrive? Again, the rational answer is no. The probability is too small to factor into practical decision-making. But there's value in the perspective it provides. It reminds us that we're all in this together, that national and cultural boundaries are trivial compared to our shared existence in a possibly metastable universe. It encourages cosmic thinking, a recognition that our ultimate fate is tied to physics and cosmology, not to politics or economics. Some might find the false vacuum depressing or nihilistic. The idea that everything could end instantly, that the laws of physics are temporary, that our existence is contingent on quantum fluctuations we can't control, it can feel like a dark vision. But it doesn't have to be. It can also be freeing. If nothing is guaranteed, then we're not beholden to cosmic purpose or grand design. We're free to make our own meaning, to decide what matters, to live authentically in the face of uncertainty. The universe doesn't promise stability, but it does offer possibility. And in this window of stability, brief as it might be on cosmic scales, we have the chance to exist, to experience, to understand, and to create. That's not nothing, that's everything. As we stand here, 13.8 billion years after the Big Bang, on a small planet orbiting an ordinary star in an unremarkable galaxy, contemplating the possibility that reality itself might be temporary, we're participating in something extraordinary. We're asking the deepest questions we can ask. What is the nature of existence? How long will it last? What does it mean to be conscious in a universe that doesn't guarantee consciousness? These aren't just academic questions. They're the questions that define what it means to be human, to be aware, to confront the vastness and uncertainty of the cosmos with minds capable of wonder and dread in equal measure. The false vacuum is still there, unchanged by our thoughts about it. The Higgs field continues to hold its current value. The laws of physics continue to operate as they have for billions of years. And the probability of vacuum decay in the next second, the next day, the next millennium remains infinitesimally small. But knowing about it changes us. It adds a dimension to our understanding of reality that can't be ignored once it's been glimpsed. We live in a cosmos where stability is not guaranteed, where the very laws of nature might be temporary, and where the future, for all its near certainty on human scales, is ultimately an open question. And somehow, beautifully, we're here to think about it. Beyond the edge of everything, we've journeyed deep into one of physics' most unsettling possibilities, from the quantum fields that define reality to the bubble of doom that could rewrite existence, from the mathematical predictions that suggest our doom to the philosophical implications of living on borrowed time. The false vacuum theory stands as a stark reminder that the universe owes us nothing, that stability is not a guarantee, and that the foundations of reality might be far more fragile than we ever imagined. What makes this possibility so unique, so different from all the other cosmic catastrophes we've contemplated, is its absolute finality. It's not just the end of humanity or even the end of life in the universe. It's the end of the possibility of complexity itself, a transformation so complete that the very concept of existence as we understand it ceases to apply. No slow fade into darkness, no time to contemplate what's coming, just an instant transition from one reality to another, from a universe where matter can form atoms to a universe where it can't, from a cosmos of galaxies and stars and planets to something alien and simple and dead. And yet, despite this looming possibility, here we are. The universe has persisted in its current state for nearly 14 billion years. Stars have formed and died. Galaxies have grown and merged. On at least one small planet, and possibly countless others, life has emerged, evolved, and developed the capacity to understand the cosmos itself. We are, improbably, living in a window of stability. A temporary bubble, perhaps, but one that has lasted long enough for consciousness to arise and contemplate its own cosmic context. The calculations suggest we might be safe, that the vacuum could be completely stable, or at least metastable, with a lifetime so long that it exceeds any meaningful timescale. But we're not certain. The uncertainties in our measurements and theories leave room for doubt. We exist in a state of quantum uncertainty, not just about particles and fields, but about the ultimate fate of reality itself. And there's something profound about that, something that speaks to the human condition in the deepest sense. We've always lived with uncertainty, with the knowledge that our individual lives are temporary and that the things we build eventually crumble. The false vacuum just extends that uncertainty to its logical extreme. Even the laws of physics, the most fundamental and reliable features of the universe we know, might be temporary. So what do we take away from this journey into cosmic fragility? First, humility. We're part of a universe we didn't create and don't control. The rules we follow are not eternal truths, but properties of a particular quantum field configuration. Change that configuration, and everything changes with it. We're not the masters of reality. We're its passengers, riding along in whatever configuration happens to exist right now. Second, appreciation. The fact that we can even contemplate these questions, that we have minds capable of understanding quantum field theory and cosmology, that we exist in a universe stable enough for complexity to emerge and persist. All of this is extraordinary. Against the backdrop of a cosmos that could have been much simpler, much more hostile, or much more short-lived, our existence is a gift. Third, perspective. The false vacuum doesn't change what we should do with our lives. It doesn't make our choices meaningless or our actions futile. If anything, it highlights the preciousness of the moment we're in. This configuration of reality, these laws of physics, this pocket of stability, they've allowed for everything we know and love. Stars, planets, life, consciousness, civilization, art, science, connection. All of it depends on the vacuum state holding, on the Higgs field maintaining its current value, on reality continuing to behave as it has. And while we have no reason to think that will change in any time frame relevant to human concerns, the knowledge that it could, that it might, that there's a non-zero probability of everything transforming in an instant, that knowledge can make us more present, more grateful, more aware of how lucky we are to exist in this particular cosmic moment. The universe is vast beyond comprehension. It's old beyond imagination. It contains structures and phenomena that dwarf our everyday experience. And beneath it all, at the deepest level we've been able to probe, lies a substrate of quantum fields whose properties determine everything else. Those fields might be in their lowest possible energy state, ensuring eternal stability. Or they might be in a temporary configuration, a false vacuum that will one day decay into something utterly different. We don't know for certain. And that uncertainty, that fundamental unknowing about the ultimate nature and fate of reality, is something we have to live with. But living with uncertainty is what consciousness does. We don't know what tomorrow will bring. We don't know how long we'll live or what the future holds. We build anyway. We love anyway. We create meaning and purpose in a universe that doesn't come with either pre-installed. The false vacuum is just the cosmic version of this same reality. We exist in a temporary state, making the most of it while we can, knowing that nothing lasts forever but choosing to care anyway. That's not futility, that's courage. That's what it means to be conscious in an uncertain universe. As we look out at the cosmos, at the galaxies scattered across billions of light years of space, at the stars burning in the night sky, at the intricate complexity of life on Earth, we're seeing the product of nearly 14 billion years of stability. 14 billion years where the vacuum held, where quantum fields maintained their configuration, where the laws of physics allowed for structure and complexity, and eventually observers capable of asking why. That's a long time by any standard. And while it's not infinite, while it doesn't guarantee tomorrow, it's what we have. It's the stage on which the cosmic drama unfolds. And we're incredibly fortunate to be here now, In this moment of stability, with minds capable of understanding just how remarkable and precarious our existence truly is, the false vacuum remains, unchanged by our awareness of it. The quantum fields that define reality continue to operate as they have since the universe cooled from its initial hot state. The Higgs field sits in its valley, stable for now, possibly forever, possibly not. And we continue to exist, to think, to question, to wonder about our place in a cosmos that might be more fragile than we ever imagined. That's the reality we inhabit. A universe of extraordinary complexity built on foundations that might not be as solid as they seem. And yet, despite that fragility, or perhaps because of it, here we are, thinking, creating, understanding, living on the edge of everything and making the most of every moment we're given. The false vacuum theory doesn't answer all our questions about the universe. It raises new ones. It challenges our assumptions. It reminds us that our knowledge is incomplete and that reality might hold surprises we can't yet imagine. But that's what makes science so powerful and so humbling. It's a process of constantly refining our understanding, of discovering new layers of cosmic truth, of confronting the universe as it is rather than as we wish it to be. And sometimes what we discover is unsettling. Sometimes the universe turns out to be more dangerous, more uncertain, more temporary than we thought. But even unsettling truths are worth knowing. Even uncomfortable knowledge expands our perspective and deepens our appreciation for the miracle of existence. So here's where we stand. The universe might be in a false vacuum. Reality as we know it might be temporary. The laws of physics might change at any moment through a quantum transition we can't predict or prevent. Or we might be completely safe, living in a stable vacuum that will persist forever. We don't know for certain, and we might never know for certain, but we know enough to ask the question. We know enough to calculate the possibilities. We know enough to confront the cosmic reality that stability is not guaranteed and that our existence depends on conditions that might not last. And having that knowledge, uncomfortable as it might be, is part of what makes us human, part of what makes us conscious, part of what makes this moment, this configuration of matter thinking about itself, so extraordinary and precious. Welcome to the universe at the edge of stability, where reality itself is contingent, where the laws of physics are properties of quantum fields that might change at any moment, where we exist in a temporary bubble of complexity, making meaning and building civilization on foundations that could shift in an instant. It's not the universe we might have hoped for, one of eternal laws and guaranteed permanence, but it's the universe we have. And in this universe, in this moment, with these laws of physics and these quantum field configurations, we're here, conscious, questioning, understanding, living on the edge of everything and making the most of every second we're given. Because in a cosmos where nothing is guaranteed, where even reality itself is temporary, every moment of existence is a gift. And that makes right now, this instant that you're experiencing, reading these words, thinking these thoughts, the most precious thing in the universe. Not because it will last forever, but precisely because it won't. Because it's happening now, in this window of stability, in this configuration of fields, in this temporary pocket of a cosmos that might transform at any moment. And that's enough. That has to be enough. Because it's all we have and it's absolutely everything.